Welcome back to a tutorial on circuit theory, and today we're here in order to learn how to solve a network, or rather network problems, okay, using Thevenin's theorem. Okay, so today in this tutorial video I'm going to show you how to mathematically solve a network problem so that you can solve all the necessary problems given in a textbook by yourself. Okay, so we're going to basically bring up our problem statement right here. Okay, there you go. So here our problem statement basically reads that, well, find the current in the 3 ohm resistor, okay, shown in the figure alongside. So this is our figure over here using Thevenin's theorem. Okay, so as you can see over here, this 3 ohm resistor right here, okay, between the terminals A and B, we need to basically find out the current that would flow through it using Thevenin's theorem. Okay, so as I've shown you in the previous tutorial on circuit theory, okay, let's bring the page a bit. Okay, that's better. So as I showed you in the previous tutorials on the Thevenin's theorem, that in order to do that, well, or rather in order to solve a network using this theorem, you gotta first disconnect the part between the terminals where you need to, or rather you're required to find the across which you're required to find the Theveninized network. Okay, so since we need to do it over here in between the terminals A and B, we're basically gonna remove this 3 ohm resistor. Okay, so that's our step 1. So I'm gonna show you the changed network right over here, so kindly hold on for a second. Okay, there you go. Here's our changed network due to the removal of the 3 ohm resistor. You can compare it with the original circuit over here. There you go. So you can see we had the 3 ohms resistor over here. Now we removed it. So now we need to basically find out the voltage that's known as VAB right over here, that develops, or rather that would basically develop in between the terminals A and B due to the removal of this 3 ohm resistor. Okay, so in order to find that out, we are basically gonna apply some sort of that KVL in order to find the voltage that would occur across the terminal A and, well, let's call this terminal over here. Okay, let's call this as terminal D, and let's call this one as terminal C. Okay, so we need to find the voltage difference that would occur basically across the terminals A and D right over here, and also the voltage drop that would occur across the terminals, well, B and C. And then if we just find the difference between these two terminals over here, we can basically find the voltage drop VAB existing between the terminals A and B. Okay, so if we just in order to solve this network, we can basically see that here's a 10 volt source, okay, connected, voltage source, okay, connected across the 5 ohms resistor over here. And now that since the 5 ohms resistor is in parallel with this 10 volt source, as you can see over here, so obviously it's quite clear that across the terminals B and C, we're going to get a drop of 10 volts. Okay, so we're going to write it down over here. Okay, so VBC equals to 10 volts. There you go. And now we need to also find the voltage difference that would exist across the terminals A and D. And in order to do that, well, it's quite a bit complex structure over here, so we need to obviously apply the KVL in order to solve this network, in order to find the voltage. Okay, so let's just assume that there would be a sort of current that would flow through this left part of this circuit. Let's just call it I. Okay, that's better, or rather I1. That suits it well. So now using this, we can basically formulate an equation over here. So let's just do that. So we're just taking, or rather we just assuming that I1 is the net current over here in this part of the circuit. So we're gonna get, well, 20, that's a 20 volt source over here, and its entire voltage will distribute across all the resistors as well. So 20 equals to I1 multiplied by, the voltage drop across this 2 ohms resistor right over here. So we're going to get, well, I1 multiplied by, well, 2 ohms plus that of I1 would also flow through this 5 ohms resistor as well. So I1 again multiplied with 5 ohms okay, and then again it also go through this 1 ohm resistor, okay, and there, sorry, there, this one got just covered right there due to the circling. That's better. So we'll also get, well, I1 multiplied by this 1 ohms resistor, and plus obviously this 5 volt that's coming from this 5 volt source, as you can see. So there you go, that's 5 volts. So if we just well, write it together, we're going to get, well, 20 equals to, well, if you take I1 common, we're going to get, well, 2 plus 5 plus 1. There you go. So actually what we are doing over here is that we can see that due to the flow of this net current in this part of the circuit, that's the I1 of course, we'll get a voltage drop that would obviously occur across this 2 ohms resistor over here. Let's call it V2 ohms. Okay, and we're also going to get a voltage drop across this 5 ohms resistor. Let's call it V5 ohms, and also a voltage drop across that of this 1 ohms resistor over here. Let's give the name V1 ohms. Okay, that's better. So we're basically gonna adding up the all the values of this voltage differences that would basically occur across these resistances that we've included in the circuit over here. So well, from this particular circuit we can understand that, well, V 5 ohms is given by, well, I1 multiplied by the 5 ohms resistance of the resistor. That's well, 5I1, and then we're going to get, well, V2 ohms is equals to, that's the voltage difference across the 2 ohms resistor over here. We're going to get it as, well, I1 multiplied with 2, that's 2I1, and of course the voltage difference across this 1 ohms resistor is given by V1 ohms, which is obviously equal to, well, I1 multiplied by 1, that's I1. Okay, so if we're just gonna look at this equation that we've got over here and then finally go forward and solve it, then we're gonna get, well, if we just bring 5 to this to the left side over here, we're gonna get, well, 15 equals to, add up together, we're gonna get, well, 8I1. So therefore from this particular equation we're gonna get I1 equals to 15 by 8 amps. That's what you get. So that's the value of I1 that's flowing on the left part of this circuit, as you can see. Okay, so that's good. And now we're basically what we're gonna do over here is that we're gonna basically find the voltage difference that would exist across that of the terminals A and D. Okay, so in order to do that, we need to find the voltage drop across that of the 1 ohms resistor and also add the voltage coming from this 5 volt source. Okay, so this over here, if I write it down as, well, VAD, then it'll obviously be, well, I1 multiplied with the 1 ohms resistor. That's the voltage drop across the I1 resistor, or rather I'll basically write it down as, well, V1 ohms plus that of the voltage from this 5 volt source, which is of course 5 volts. Okay, so if we just go forward and add it together, then, well, V1 ohms is equals to, well, that of I1. Okay, that's good. That's I1 volts, obviously. So and the value of I1 is, of course, as you can see over here, 15 by 8 amps. So if you just go forward and put it over there, well, 15 by 8 amps multiplied by 1 ohms. Okay, plus that of 5 volts, so we're going to get, well, 15 by 8 volts plus 5. So that would obviously give you a result of equals to approximately about, well, 6.875 volts, as you can see. Okay, so now that we have already found out the voltage difference across this the A and D terminals, as well as we know the voltage difference across the B and C terminals over here, we could simply, well, find out the voltage drop, that's VAB, that would obviously occur across the terminals A and B. So by applying basic laws of circuit theory, we're going to get, well, VAB is equals to, well, VAD minus that of the voltage difference existing between the B and C terminals, that's VBC. So here VAB is obviously 6.875 volts minus that of, well, VBC is 10 volts, as you can see over here. So we're going to put it over here. There you go. And now this result would be something like, well, minus 3.125 volts. There you go. So we can see over here that, well, the terminal B is at a higher potential compared to that of the terminal A. So obviously that's why VAB is negative, as you can see. Well, so okay, so that's done over here, and now finally, since we need to find the current through this 3 ohms resistor over here, we also need to find the net voltage, or rather, I mean, sorry, the net resistance. That's the RTH, or rather net Thevenin's resistance that would obviously be offered by the rest of the network, okay, across this 3 ohms resistor. So if we go forward in order to find that, so we're basically going to go to step number 2. So this was our step 1 so far. Now in step 2, what we're supposed to do is that we're supposed to, well, short all the voltage sources in the network and, well, open if there are any sort of current sources. Okay, so in that way our network would basically change to something like this, as you can see. Okay, so if you compare this diagram with the original one, so you can see, well, here it is. So you can see over here that this was the original circuit, and now what we have done is that we basically shorted all the voltage sources. So since there are no current sources in the network concerned, so well, we need not think about them. So if we go forward, well, here is the network which we are going to obtain. But wait a moment. We can see over here, well, yep, on the left part of this network, well, we can just go forward and obtain the net resistance, all right. But if you take a look over here in this right part of the network, we can see that, well, there is a short circuit. So obviously it's quite natural that the equivalent resistance generated, or rather that would basically be found out for the terminals, I mean in between the terminals, well, B and C, okay. If we just go forward and find out the equivalent resistance over here, since there's a shorted path, so we're basically going to get the net resistance across the B and C terminals as equals to 0. So our B and C, so that's RBC right over here, is equals to, well, 0 ohms due to the existence of this shorted path, as you can see over here. So this is of course a shorted path right over here, as you can see. Well, so in order to well, deal with this one, okay, we need to just, well, eliminate this part of the circuit so that we'll only have the terminal B, since the net resistance would be 0. So that obviously happens when there is a shorted path in parallel to a resistor. So we're basically gonna well, remove the 5 ohms resistor since it's of no use, as you can see from this diagram over here, and that would basically bring us to, well, step number 3, as you'll basically find out shortly. And finally we're here at step 3, and well, this is our modified network from that of step 2. If we just compare both of them, you can see over here that, well, due to this shorted path, the entire resistance was 0 in that, I mean, existent across the terminals B and C. So what we did is that we basically, well, removed the 5 ohms resistor since it's of no use, and the equivalent resistance across the terminals B and C is still 0 ohms even if we included the 5 ohms resistor. So we just, well, cut out the unnecessary complications. So here we are, and we can also see that, well, the 5 ohms and 2 ohms resistor were in series, so we could basically, well, add them up together. So if we did that, then we're going to get, well, 7 ohms. So what we need to find out is that we need to find the net resistance that is existing across the terminals A and B. So we can see that the 7 ohms and 1 ohms resistances are there in parallel. So we can go forward easily and find out their equivalent resistance. So we're going to get, well, R equivalent as equals to, well, 7 ohms multiplied by 1 ohms divided by 7 ohms plus 1 ohm. So that's the equivalent resistance that would exist across the terminals A and B, since 7 and 1 ohm are in parallel to each other. So that gives us, well, 7 by 8 ohms. So if you express that in decimals, we're basically going to get, well, 0.875 ohms. There you go. So with this, we just finally reach the stage where we can obviously, well, get our equivalent network using Thevenin's theorem. So finally we're here at step number 4, and here I'm gonna draw the equivalent Thevenin's network. So as Thevenin said that, well, any network could be simplified to a basic voltage source in series with a resistor. That's obviously the equivalent Thevenin's resistance. So we're going to include a resistor right over here. Okay, there we go. And now we also going to include a voltage source. Okay, so where is the voltage source? Okay, I'm going to draw it right over here. So there you go, that's a voltage source. And now if let's just add the necessary signs over here. Let's wire them up together. Okay, there you go. One ends up, and there you go. And now what we have over here is that we basically have the terminals A and B right over here existing, as you can see. Well, and we can basically connect the 3 ohms resistor somewhere right over here. Okay, so now the 3 ohms resistor, well, it would basically, behave as our load resistor, since we are finding out the necessary equivalent Thevenin voltage and resistance across its terminals. So here we have the Thevenin's voltage, so let's just call it VTH, and here's the necessary Thevenin's resistance, that's RTH. Now the values of the Thevenin voltage have been found out in step number 1, which you can see right over here. That's 3.125 volts. So we can go forward and put that here with ease. So we can see that, well, it's 3.125 ohms. That's VAB. Obviously it's a negative one. Okay, so now over here the value of the Thevenin's resistance, as we found out, well, it's 0.875 ohms. So we can just write it over here, well, 0.875 ohms. Okay, and this is our 3 ohms resistor, which we had previously removed from across the terminals A and B. And now if we just find out the current that's going to flow through this 3 ohms resistor, so let's just assume that we're going to get a load current IL flowing through the 3 ohms resistor over here. So with that kept in mind, we can just find out the value of IL, which would be given as well VTH divided by, well, RTH plus that of the RL. So this is RL, that's 3 ohms resistor. Okay, so if we just go forward and put their values concerned, well, 3.105, and then okay, and then we're going to get 0.875 plus that of 3 ohms. So we're going to get, basically we're going to obtain a value of about 0.807 amps. Okay, or rather we can also write it as well, approximately 807 milliamps of current should flow through this particular 3 ohms resistor. Okay, so now that we have finally solved our network using Thevenin's theorem, you can basically, well, go forward and apply this theorem to all sorts of problems regarding this theorem, and happy journey throughout. So that's the end of this tutorial video. Hope you've enjoyed it, and don't forget to watch our next tutorials as well. So it's just a short goodbye for now, and thanks for watching.